Welcome back, everybody. Today we're going to touch on a couple subjects, some models of the solar system, and if we have some time towards the end, we're going to talk about time. So first, let's start out. Now, back in the day, a long time ago, people thought that the Earth was at the center of our solar system. They didn't really know any better because everything seemed to go around it, the sun, the stars, the moon. And so, hey, we didn't feel like we were moving. Might as well be at the center. This was first proposed, I believe, or at least recorded by Ptolemy. And this Earth-centered solar system model is incorrect. We know that, obviously. But it survived until the 1500s. And this picture on the right kind of shows it best with the nice artwork. Earth is in the middle. There's the moon, Luna, Mercury. I believe that's Venus. Solus, the sun. Then Mars, Jupiter, Saturn, and beyond Saturn, they didn't know about Uranus and Neptune or Pluto or anything, was the background field of stars. And these stars went around and around and around. This is the model more simplified, the Earth in the center, and the planets doing these little tiny motions here as they orbit around Earth. Remember that little small movement those planets make. We'll get to that later. Now, in the 15 and 1600s, three men, Nicholas Copernicus, Johann Kepler, and Galileo Galilei, proposed a new model. Copernicus really was the one who initiated it. This was the sun-centered model. Now, we know this is obviously correct, but it explained the motions of our sun, the planets, moons, and stars. Remember, helio means sun, geo means earth, so heliocentric, sun-centered, geocentric, earth-centered. But in this model, Earth must rotate and revolve in order for it to work. And this is why it was so hard to sell to everybody, because we didn't feel like we were rotating, 1,000 miles per hour. So we didn't feel like we were revolving through space at hundreds of thousands of kilometers per hour. Turns out we are. And in this model, you can see sun's in the middle, Mercury, Venus, all the planets going around and around and around and around and around in their orbits. Earth's moon going around Earth. And here's a more artistically drawn version of it. You notice the sun doesn't look too happy there. Can't quite figure that out. And beyond all that, you'll see the constellations. There's Cancer, the Crab, and Gemini, and so on and so forth, Taurus. Now, after Copernicus proposed heliocentrism, Johannes Kepler used Tycho Brahe's precise data and his ellipse to perfect the model. Now, Galileo Galilei built this simple telescope, and he had heard about some lenses in the Netherlands. So he put some together in a tube and made a rudimentary telescope. And this is what he saw on January 7th in the year 1610. Jupiter and moons orbiting Jupiter, changing position day by day, actually night by night. They're actually called now the Galilean moons. Now, his argument was that if these objects orbited the planet Jupiter, then how in the world could they be possibly orbiting the Earth? And if that's the case, we're not in the middle. This shattered the established geocentric model, and it stirred up controversy within the church. You guys might already know the story with what happened to Galileo after that. So, some support for the heliocentric model. Remember, in order for it to work, the Earth needs to rotate and revolve. And this took time for other people to believe because they didn't feel the Earth moving. They thought the birds would be flying in one direction. There'd be a constant wind blowing from one direction all the time if the Earth were spinning. But one of the things we did know at that point was that a free-swinging pendulum, the Foucault pendulum, makes a circle, makes a kind of a complete motion throughout a day if you're at the North Pole. But, if you're farther south towards the equator, it changes. We'll get to that in a moment. It also accurately predicted where the planets should be. It was more accurate, although they did kind of finagle the geocentric model to make it close to accurate. But the heliocentric model was better. And finally, the heliocentric model was just so much simpler than the geocentric model. It didn't have all those little tiny movements of the planets. the epicycles. So in the end, Galileo was right. He was right in a number of ways. This was just one of them. And here's a nice photo showing Leon Foucault's pendulum in Paris. Another more close-up. This is actually, I think, an artist rendition. And it knocks over the pegs. Different museums around the world, it's great to watch the kids gather around and watch it get closer and closer to one of the pegs, and then as it knocks it over, everyone's, oohing and ahhing, and then they leave for a while until it gets close to the next one. Then at the end of the day, someone has to set them all back up again. So evidence for rotation. Freely swinging pendulum will swing back and forth while eventually making a complete circle. And this would not happen if the Earth didn't rotate. Now some side notes to this. At the North Pole, the pendulum does make a complete circle every 24 hours. And that has to do with the fact that the North Pole is perpendicular to the equator. The polar axis is perpendicular to the equator, so the forces are acting at full strength. But at 43 North, where we're located here, it takes about 35.3 hours to do the same thing. Now at the equator, where the forces are actually parallel to each other, so they're not affecting each other in the same way, it will not work at all. The pendulum doesn't make this loop. Now, rotating Earth supports heliocentrism, and we already know this from the reference tables, the Earth's period of rotation. Little fun fact, at the equator, the Earth's moving about 1,600 miles an hour, kilometers per hour. Pretty darn fast. We don't feel it because we're all moving together. At the North Pole, it's 0. Okay, some more evidence for heliocentrism. I got to throw this in here because it is a good piece for me at least. The Earth revolves around the sun. We know that once every 365.26 days and in an ellipse. But how do we know it revolves? Well, one of the reasons is the seasons. It really conveniently answers why we have the seasons. Earth's tilt would only cause seasons if Earth changed positions relative to the sun by revolution. Now the other thing with the seasons is that during different seasons we can see different constellations. They're only visible certain times of the year. And it's evident in this left-hand diagram where we see the constellation Scorpius can be seen by the Earth here in June. We cannot see Scorpius when Earth is over here in January because the sun's in the way. So Scorpius is there, it's just blinded by the sun. And the opposite's true 6 months later. So different constellations disappear. Not all constellations do this. The ones near the North Star, they're up all year round in the nighttime. But you get the idea. And over here in this right-hand diagram, you can kind of see how that works. The summer sky constellations, when the Earth's over here, you can't see Leo, you can't see Cancer, you can't see Virgo. But when the Earth's over here, you can see these three constellations because the Earth's on the same side of the sun. So the sun's not blinding them. They're out at night. Okay, some more evidence for revolution. We know that because we go around the sun, we get a little closer, a little farther, and so the apparent diameter changes. Remember aphelion, farther away, perihelions when we're closer, so the smaller picture is aphelion. Now, the old geocentric model had a way of explaining this too, but it was just too complicated. So make sure to review the differences between the geocentric and heliocentric models of the solar system. Know the evidence between the two. Okay, now we do have a little bit of time to talk about time. So let's just briefly mention some of these things. Some of this you already know from before. Time is mostly based on motions of our Earth, but also we do include motions of the moon in there for the month. Speaking of the month is based on the number of days it takes to go from full moon back to full moon again, or new moon to new moon. And they call this the moonth, or the month. That's where it comes from. And you can see in the bottom diagrams, from new moon back over to new moon, which is off the page just a little bit, would be 1 month, or 1 month. It's about 30 days, 29 and a half to be exact. Okay, the next thing, time, it's based on the real motions of the Earth, our rotation, and apparent motions of the sun. You know, the arc-shaped path we learned about from east to west, 15 degrees an hour, the one that was beat into your heads over and over and over again. And I know some of you have played with these sundials before. I have one in the classroom. That's called the gnomon that creates the shadow. Now, some problems with local solar time is if we all use sundials to tell time, we're at different longitudes on the Earth. And that means that the sun's at a slightly different spot when it's at its highest point in the day. So that means our 12 o'clock noon is going to be different everywhere at different longitudes. Not for latitudes, but for longitudes. And that's not good for modern life, you know, where we travel around real fast. The local solar day, it's the time from local solar noon to the next local solar noon. And local solar noon is the time when the sun's at its highest point in any given place during the daytime. And it's usually not 12 noon. Sometimes it is, but most of the time it's not. So when the sun reaches its highest peak right here, we call that the transit time. That's at local solar noon. And that's when the sun moves from AM to PM locally. Now, mean solar time means the average solar time. And this is a 24-hour day. We round it 24 hours and 365 days for 1 year. Mean solar day, mean solar noon, 12 o'clock noon. And the time zones we already talked about way back in Unit 1, 15 degrees wide, because that's how fast the Earth rotates. And just remember that the average solar noon, the mean solar noon, is, 12 o'clock is not the same as local solar noon when the sun's at its highest point most of the year. And that's just because of this, equation of time, which we'll talk about, and I have a little applet to show you. This is great just to show you guys the 24 different time zones, 24 different red lines here we talked about in the last lesson. Each one's an hour apart. And they're, of course, average. The real time zones zig and zag around different countries, different states. And in this applet, if I could get this to work right, I want you to watch over on the left at that figure 8 looking red traced path. And that shows the analemma. And then at the bottom of the screen, where it says equation of time at the very bottom towards the center, it says minus 631. And when the sun is on the right side of its meridian, which is where south is, it's going to be negative equation of time, and when it's on the left, it's positive. So as I slide the months along, you should see during August, the sun starts to move to the left side, and we have a positive equation of time. And that just means that our local solar noon is ahead of our mean solar noon. And I can go backwards and show it the other way too. So the sun is not always at noon right on that center south facing line. It's usually off to the left or off to the right. And where the figure 8 crosses at the very top, in the middle, and at the very bottom, that's when it's actually like, mean solar noon is local solar noon, but it doesn't happen that often. I can play this thing too so you can see it throughout the year, or you can go throughout the day. Let's let the sun come back around. And let's change this to daytime. And now we can step it day by day. You should be able to see that sun. Actually, let's get it right on noon here. I think this will show it best. Okay, now you can see definitely how the sun is ahead of, in this case behind, and now ahead of to the left of that meridian line, that white line going straight down towards the south. In different months, it's either ahead or behind. This is called the analemma, and it's based on the equation of time. All right, hope you guys learned a little bit about time. Speaking of time, it's the end of our time, and also about the two models of the solar system. See you next time.